Hi, I'm Dr. Iman Chakraborty. I'm an assistant professor at Auburn University's Aerospace Department. This paper has been authored by my graduate student Ashutosh and myself, and we've analyzed a lift plus cruise VTOL aircraft with electrified propulsion systems. This is the aircraft concept that we've sized and analyzed. It's a lift plus cruise concept which has 8 lift propulsors that are mounted on booms, and they provide the thrust for vertical flight mode. It's got a single pusher cruise propulsor that provides the forward thrust for forward flight mode, and it uses a combination of conventional control surfaces as well as propulsors as control effectors in vertical flight mode and forward flight mode, with a smooth blend between propulsor-based control in vertical flight mode to control surface-based control in forward flight mode. And we've sized this aircraft based on a representative urban air mobility mission that you see over here. To size this aircraft, we've used the Parametric Energy-Based Aircraft Configuration Evaluator, or PEACE tool, which is a tool that we've developed in our lab. And in prior work, we've shown that this tool is able to deal with flight vehicles that use wing-borne lift, rotor-borne lift, buoyant lift, or combinations thereof, and also aircraft that have conventional fuel burning propulsion system architectures or electrified propulsion architectures, which could be all electric or hybrid electric. The different modules of this framework, which you see on this chart over here, are described in pretty good detail in the paper. To analyze this aircraft, we've used a strict theory-based approach where all the lifting surfaces are broken down into span-wide strips, and then the loads on each of those strips are built up and then summed to give the net effect of all lifting surfaces on the aircraft. For the propulsors, we've used a blade element momentum theory-based approach, which is coupled with the Pitt-Peters dynamic inflow model, and that basically discretizes these lift propulsors and builds up the loads on the lift propulsors in that manner. Other parts of the aircraft geometry, like the fuselage or booms, we use lookup tables in order to characterize the loads developed on those bodies. And we add all of this together to get the net aeropropulsive effect on the aircraft in flight. This shows the propulsion system architecture in some more detail. So this is a hybrid electric architecture. So there are 2 power paths. There's a battery power path and there's a turbogenerator power path. The battery power path is just batteries putting power into the lift and cruise propulsors. The turbogenerator power path comprises a turboshaft engine that drives a reduction gearbox that drives a generator which generates electricity and puts it into the lift or cruise propulsors. On the right, you have a power flow matrix, which is basically a matrix representation of the power flows across each of the individual components in this architecture, as well as some closure relationships that determine what happens when power arrives at a node like this and then splits in 2 directions. How much goes in which direction. The idea is to be able to invert this power flow matrix and thus be able to solve all the elements within this vector over here, which are the individual power outputs of different propulsion system components. We do this for 2 reasons. We do this during mission performance analysis to be able to assess how much energy is consumed over the course of the mission. And secondly, we do this during power sizing, where we evaluate this power flow relationship over various nominal and off-nominal scenarios to see which of those scenarios ends up sizing which of the components within this propulsion system architecture. One of the first things we analyzed was the effect of wing loading, disk loading, and cruise speed on the sizing results. And this chart shows you that for the all-electric architecture. So in general, when there's an increase in cruise speed, there's an increase in propulsive power requirements, and typically that's going to result in an increase of maximum takeoff mass, which you see over here. When wing loading increases, initially there's a pretty substantial reduction in maximum takeoff mass, as the reduction in wing area results in some weight savings and also some drag reduction. But once you get up to about 50 pounds per square foot wing loading, it's a point of diminishing return. So increasing the wing loading beyond that isn't really going to have that kind of an effect. For disk loading, there's a pretty well-defined bucket. So there's a sweet spot around 20 pounds per square foot hover disk loading. that seems to minimize the maximum takeoff mass, and there's an increase in maximum takeoff mass on either side of that sweet spot disk loading. This chart shows you how the sizing results for the all-electric, hybrid electric, and turbo-electric architectures change as you size them for a range of single trip distances, as well as varying technology state-of-the-art for batteries, represented by battery-specific energy, as well as battery C-rate, which ultimately changes battery power density. So if you look at the all-electric architecture, there's a pretty severe sensitivity of a maximum takeoff mass to trip distance. And even though the maximum takeoff mass falls with improving battery technology, that's still a pretty steep relationship. For the hybrid electric architecture, it's a much more gradual change of maximum takeoff mass with increasing trip distance, because the hybrid uses the significantly more energy dense fossil fuel that the turbo generator power path consumes to develop the power that's required for forward flight mode. And if you look at the turbo-electric architecture, that obviously uses only turbo generators in its propulsion system and doesn't really use batteries, as a result of which it's unaffected by the technology state-of-the-art of batteries. That's why you see only a single gray line here for the turbo-electric. The jump from the solid line to the dotted line of the same color represents what would happen if the C-rate of the batteries were to be increased from a C-rate of 5 to a C-rate of 7. And what that's basically doing is it's improving the power density of the batteries. And the effect is very significant for the hybrid architecture, whose batteries are sized by peak power requirements and not energy requirements. So when you have an increase in C-rate, there's a pretty substantial improvement in maximum takeoff mass of the hybrid architecture. This chart shows an all-electric, a hybrid electric, and a turbo-electric architecture that have been sized to the same maximum takeoff mass of 2,800 kilograms. And the intent here is to be able to analyze what is that mass made up of for each of these different architectures. So each of them has the same payload of 400 kilograms across the board. And if you look at the structures and systems weight for the three, you'll see that they're pretty similar to one another. Where they differ is in the propulsion system weight fraction. For the all-electric, this comprises the lift propulsors, the cruise propulsors, their motors, and also power cabling. For the hybrid architecture, this includes, in addition to all of those, the turbo generator systems that are responsible for the turbo generator power path. And for the turbo-electric architecture, it has 3 turbo generators as opposed to the hybrid's 2 turbo generators. And those are sized by a high altitude hovering requirement where the turbo generators have already lapsed in terms of their power availability. So as a result, the upsizing that needs to happen for the turbo generators for the hybrid as well as the turbo electric result in significant increases in the propulsion system mass fraction. The all-electric's batteries are sized by energy requirements, and because the specific energy of batteries is relatively low at present, you have a large percentage of battery mass for the all-electric. The hybrid electric's batteries, on the other hand, are sized by peak power requirements and not energy requirements, as a result of which there's a significant reduction in battery mass fraction for the hybrid. And the turbo-electric, of course, doesn't use batteries in its propulsion system architecture, so there's no battery mass on it at all. This chart explains the difference in the sizing result for the hybrid architecture if a reduction in payload at high hot conditions, so high density altitude conditions, was allowed versus not allowed. So in this column you see how it would size if 75% payload was carried under such circumstances, and in this column you see what would happen if 100% or the maximum payload was carried. And what you see over here is a significant upsizing of almost all the components in the propulsion system architecture. This is explained in a lot more detail in the paper, so I encourage everybody to refer to the paper for that. Thanks everybody for your attention, and I hope to see all of you at the conference. Thank you very much.